Welcome to the newly added Chapter 6. This is a chapter on the RISC-V assembly language, which as of 2024, in fact, I'm recording this video on the Christmas day of 2024. RISC-V is very popular and it is projected to be one of the most popular instruction sets, especially RISC instruction sets, in the near future. So this is a part of the second version of my book, Basic Computer Architecture. The entire book is available for free at my homepage and also accessible at this URL. So remember to put an HTTP and not an HTTPS. So the S causes a problem, so it's just HTTP. So you can download the full PDF of the book, including this RISC-V chapter. Links to the YouTube videos, which is basically this video that we are recording. The slides, the software, and the solution manual, everything is available on this website. And the print version for people like me who prefer print books is available worldwide via White Falcon and Amazon. So you can go to your local Amazon site and you would find a copy of this book. And this can be purchased. The print version, the PDF version is free, absolutely free. It will continue to be free. And any updates we'll continue to incorporate in the PDF version of the book. So here is what we will do. We have 5 broad sections. So we have the RISC-V machine model that we'll discuss first. So we always do that. And given the fact that in this book we have already covered 3 assembly languages, so if you would recall, so we covered simple RISC, right, which is a very simple RISC ISA that we designed. Then we covered the ARM assembly language and finally x86. So some amount of familiarity of assembly languages is assumed. So in case there is a problem, you can go to the the simple RISC chapter and kind of go through the same concepts again. So because this is the fourth and the last assembly language that is being introduced, the treatment is slightly brief, right? So many details have been abstracted out because in the last 3 chapters they have kind of been discussed in depth. Any doubts, you go here to this chapter, right, which is the basic assembly language chapter. So we will discuss integer instructions, memory, control transfer instructions, floating point, and finally the encoding. So there's a little bit of a change in the slides, so new technology keeps coming. So we used code snippets that were beautified with the Carbon app. So that is available at this website here. So we are more than thankful and grateful to them for having this wonderful website. So all the code snippets that you see have been beautified with the app that is on their website. So without further ado, let's discuss the main reason for having a modern ISA. So you need to understand that, from starting of this millennium, no one really thought that an ISA is something that is important. People thought that the field of ISA design is mature and there is no need to design a newer ISA because in any case you had x86, which was kind of the market leader. It had all CISC features. Then you had a bunch of RISC ISA starting from the PowerPC ISA, UltraSpark, right, for Sun. Then of course you have ARM, which is very common. So nobody felt a need for an additional ISA, right, because you have so many. So it turned out that for both technical reasons as well as legal reasons, right, both are important. Because the ARM ISA, for instance, is licensed by ARM, 2 companies. So in a certain sense, it's a proprietary product. So there are reasons why there was a need to design an ISA which was open. In a sense, anybody can build a processor for that ISA. A few additional requirements: it had to be compatible with all kinds of devices. starting from small 32-bit devices, in fact, also 16 bits, 64 bits, 128 bits, right? So you want it to also be compatible with servers. No licensing requirement. This was a huge requirement, primarily because many of the proprietary ISAs did not allow a vendor or a company to build a processor for that ISA without paying a licensing fee. And depending upon whom you ask, many would say that the licensing fee was quite high. Second, it is necessary to build an ecosystem around the ISA, so you need a large software developer community. So they would create all the bin utils like your assemblers and object dumps and static library linking routines, dynamic library linking routines, and then of course compilers, and then someone has to port the Linux OS to RISC-V. So a lot of work had to be done. So given that so much of work had to be done, nobody wanted to invest in something absolutely new. But clearly there was a requirement for that. Number one, because a lot of things had been learned over the years. So from a technical and technological perspective, a new ISA was needed, right? Because as I said, the learnings had to be incorporated. Second, many kinds of new accelerators were coming up, and some ISA support was required, right? Maybe as an extension. So vector extensions, cryptographic extensions, AI, ML, and so on. So the main idea was to sort of create some sort of a modular ISA where you have a base set of instructions, and then you sort of have these, add-on modules that you can add depending upon the requirement. So looking at this entire complex landscape, right? So you need to understand that designing a core stopped being rocket science, let's say by the late 90s. So even university groups and mature developers could design a core. They had the financial resources to fabricate it. But the reason they needed their own ISA was primarily because they needed access to a developer community and some sort of an ecosystem. So Berkeley tried to seed that ecosystem in 2010 by creating this effort. And in 2015, all the documents were released under the Creative Commons license, which is a reasonably permissive license. And now RISC-V is maintained by the RISC-V Foundation, which essentially encourages open source hardware and software development based on RISC-V. Let us now look at the RISC-V machine model. So in RISC-V, we have different ISAs actually. So it's not one ISA, but it's an ISA with many flavors, extensions, and variants, right? So this is not something that we may be used to because whatever we have seen up till now has kind of been a single monolithic ISA. But the point is that this is not like that. So the base ISA is RV32. So as you can see, RV32 is the base, which basically means it has 32-bit instructions and that too the basic set. Then there is an embedded version. So the embedded version, as we shall see, is somewhat restricted in what you can do and what you can use. So it's made for smaller embedded processors. Then for large server class machines, there is the 64-bit ISA, which again comes in two variants, right? So you can have a 64-bit ISA for a server class machine and an embedded variant, particularly for high performance embedded systems. And then, of course, a 128-bit ISA where the data path is really wide. So this is mostly for SIMD kind of instructions where we want to pack a lot of data items in the same memory word. So as of 2024, RV64 and RV128 are not very mature, but RV32 is very mature. And with all these instruction sets, we can have a lot of these extensions. So for instance, we have already seen the E extension for the embedded version. The I extension is standard, so most of the time this is not written because you sort of assume it's there. Is the base integer ISA that has very basic integer instructions and load store instructions. Then we have the M extension, which is primarily for multiplication and division, because these are not a part of the base ISA. They are not a part of this. They are separate. Then if we expect that multi-threaded programs will be run or there'll be some kind of multiprocessing. So even if you run single-threaded programs, but you have the Linux kernel, then that does still have, multiple processes that are running at the same time. So it would still need support for atomic instructions. So this is in a sense considered standard, in the sense that even if you are not actually into parallel processing, you'll still run a multitasking kernel. And the multitasking kernel would need internally atomic instructions. So supporting this, so I, M, and A are sort of standard. A lot of codes may not use floating point, so there is no need for single precision floating point or double precision. There's no need unless you're using them. The same holds true for vector instructions as well, that there is no need for them unless we are into something like matrix multiplication or AIML kind of codes. So then vector instructions are needed. So if we talk more about extensions, as we have seen, RV32I, which is the integer extension, let me write it down. This is standard. So this is something that we have, and this is the regular 32-bit ISA. RV64I and RV128I are also there, and they are maturing. And also what we discussed is that the standard set is integer, multiplication, division instructions, and atomic instructions. Furthermore, given an ISA with its extensions, let's call it ISA++, you can have basically a major revision, a major version, because the specifications keep changing, right? So you can have a major, and then P is a delimiter, and then you can have a minor version, right? So if I write RV32I1P3, then the major version number is 1, minor is 3. So what happens is that the RISC-V consortium periodically, on a regular basis, issues new specifications. So new versions of the ISA are released periodically, with minor changes and tweaks. So the expectation is that hardware designers and also software writers who are writing the software stack would update their stack accordingly. And most changes are, in a sense, backward compatible, which basically means something that was already executing will continue to execute. So sometimes what we do is we take a bunch of these extensions. So let's say, you have the integer extension, some additional integers, additional integer instructions, the floating point extension, the synchronization instructions, that extension. So you take a bunch of these extensions and you sort of group them and you create a master extension G. So RV32G thus becomes the most popular format for a large number of processors where G is not one extension, but rather it is a collection of many different extensions. So it is a collection of the integer instruction extension, the floating point instructions, atomic synchronization instructions, so on and so forth. So now the question is that what if we run out of letters? Because if you see here, we have single letters and there are only 26 such letters. So that is why the Z or Z series was introduced. So what you can do is that you can do this and then you can write a lot. So let's say if I write FA for instance, These are additional floating point instructions. You can have additional integer instructions, right? Additional memory instructions and a lot of that. So in a certain sense, this is like an expander for extensions where you can create a lot of custom extensions. And this will ensure that the ISA is sort of rich, but it is not necessary for any one implementation to support all the extensions. Just support the standard ones and the ones that you need. So now let's come to the embedded and compressed versions. But before we talk about them, we need to understand that the instruction width has been set to 32 bits even in wider formats, like even when the data path is 64 or 128 bits, which basically means that the register size and the memory address size is 64 or 128 bits. The instruction size has still been kept to 32 bits for the sake of compatibility, ease of use, and so on and so forth. But sometimes there is a need to actually have smaller instructions or use fewer instructions in the extension or use fewer registers. So this is mainly to reduce power and to also have a smaller implementation of the RISC-V processor. So in this field, two versions stand out: the embedded version, right, or the mnemonic E, and the compressed one C. So here what happens is that we do not reduce the instruction width, it still remains 32 bits. So incidentally, people are thinking about having a wider RISC-V ISA, of having maybe a 48 or 64-bit ISA. So you can go to the RISC-V site and you will see that there are some standards that are sort of being built around this, and they are at different stages of maturity. So you can keep tracking. So maybe when you know you are looking at this video, perhaps it would have been released, but at the moment, so this is 26th of December 2024, these standards have not been fully ratified. So let's now come to the compressed version. So the compressed version, we actually reduce the width. So we actually reduce the width from 32 to 16. So this reduction is done. And instead of accessing the full set of 32 registers, we actually access only 8 registers, right? So we don't access the full register set, right? So RISC-V has, it's a RISC instruction set, so it has a lot of registers, but we access only 8. Also, the instructions and opcodes that are supported is kind of limited. And RISC-V supports in general 12 or 20-bit immediate values, but in the compressed form, it is actually much smaller. So this is for ultra small and ultra low power processors. They are the ones who would actually benefit from the compressed version of the ISA. So now let's take a look at the integer registers. So there are 32 registers as we have mentioned. So the first register is called X0. So incidentally, the registers have two names. The registers are either X0 to X31. That's one way of addressing them. The other way, which is actually preferred, right? That's the way it should be, is by mnemonics. So which means that you give it another name. The other name is suggestive of its function. For example, assembly languages have a very, very strict usage convention, and that is something that assemblers, compilers, everybody follows. The mnemonic, in a sense, represents and carries that convention. So you will know when to use which register, when not to use it, and the mnemonic makes it very clear. So the first register is called X0. This is a very, this is a novel concept. This is new to RISC-V. So we have not seen this earlier. So this register is known as the 0 register because it is hardwired to 0. So we will see there are a lot of uses of this register. And it is extremely useful starting from moving values to whatnot. But when we look at this register in use, we'll realize its power. The rest are sort of standard in the sense x1 is the return address, and so it is called RA. X2 is the stack pointer. We have seen that. X3 is the global pointers. This is like stack pointer at the top of the stack, and this is like the bottom of the activation window. Then we can have a thread pointer, which actually points to a local storage area of a thread. So if I consider a thread, it will have some area where it stores its private variables, that is TP. Then we can have x5 to 7, which is also the mnemonics T012. So these are temporary registers that are meant to be used inside a function. They are not saved. So they are not caller saved or callee saved. Sorry, I just stand corrected over here. So I would just like to amend what I said a minute ago. The global pointer is actually a pointer to a region of global variables. So sometimes what happens is that all the global variables are stored in one location. So the global pointer in a sense points to that location. And this is useful especially if we have a lot of global and static variables. So then we will have this one register that holds a pointer to that. And this is particularly very useful in large programs, starting from operating systems to reasonably large pieces of software where access to some global table is needed all the time. So then we have, let's come back, we have temporary registers that are not saved. And then we have the register S0, which is a saved register. So this is the frame pointer, right, which starts kind of the current frame, current, what is also called an activation block, right? So essentially the area of the stack that stores the state of the current function's execution. So S0 can act like a regular saved register or like the frame pointer. Then X9, which is S1, similarly is a saved register. And then we have a bunch of registers. So we actually have 8 registers starting from X10 to X17. So which are for function arguments and return values. Specifically, A0 and 1 can store both arguments as well as return values. The reason that 2 registers are provided is because let's say we have a 32-bit ISA and we want to return 64 bits. As is often the case, sometimes we multiply and the product is 64 bits. So that is why 2 registers have been provided. And then the rest are for function arguments. So we have a sufficient number of registers for function arguments. Then we have a few more registers that are meant to be saved across function invocations, S2 to 11. And finally, a few more temporary registers. So as we can see, we have 12 saved registers and 7 temporary registers from T0 to T6. So the temporary registers are not saved, but the S series are saved. So essentially, other than these special ones, where 0 is super special, we have 3 series of registers. S is the saved series, T is the temporary series not saved. Then we have A, and A is for arguments and return values, where A0 and 1 are for return values as well. So we can refer to registers in assembly code using their mnemonics or using these register names x1, x2, x3. So just to remind you, x0 is hardwired to 0. It's also called the 0 register. There is a dedicated PC register which cannot be manipulated directly, but it sort of can be indirectly accessed. This is a bi-endian ISA in the sense you can choose whether it is little endian or big endian. It is a bi-endian ISA. That is another strength. So as I said, whenever you do something new, you learn a lot. You incorporate whatever you have learned. And this is exactly what has been done in the case of RISC-V. Let us now take a different look at the space of registers. So we have already said that there are 32 registers in the RISC-V instruction set, and for RV32 there's 32 bits each. For RV64 each one of them is 64 bits, as you can see. So it's just that the register becomes wider. So recall that in x86 also we had a similar concept where the registers used to become wider as the data path size increased. And then RV128 is when the register becomes even wider. The PC, as I said, is a register which cannot be directly manipulated, but it can be indirectly manipulated. And that too has different sizes based on how wide the instruction set is. So we'll now come to our second part, which is the main integer instructions. So let's take a look at the quintessential instruction, which is moving a value to a register, right? That's maybe the first thing that anyone would do while writing an assembly program, or moving the content of one register to another, which is again something that one would do. So this is where the greatness of the 0 register comes in handy. So the add I instruction is essentially add immediate. As you can see, the I stands for immediate. This has exactly the same semantics and the same format as the other RISC instructions that we have seen. RD is the destination, RS1 is the first source, IM is the immediate. For example, if I am adding a register and an immediate, so then it will become the contents of x0, which in this case is 0, plus 5, and that is transferred to x1. So let me tell you, in case you have not noticed, that adding the immediate to 0 and then transferring it to a register is nothing but moving the contents of the immediate to the register. So in the sense that we do not need a separate move instruction, this is not needed. Everything is folded, and that too, very intelligently folded into the same add immediate instruction. The reason being that one, you can use x0 or the 0, or you can also write 0 here, the 0 register. Anything added to 0 is essentially that number. So that is being transferred to the destination register, which is over here. So this is tantamount to moving the value. Of course, you're not forced to use x0 here. Any other register can be used. In that case, we are simply adding the immediate value to the contents of the register. It's not moving, but we are kind of incrementing it by whatever is the value in the immediate field. So this is one way of kind of getting rid of one instruction. Also, we do not need a sub I. A sub I instruction is not needed because the immediate is signed. So then there is a generic form of this, which is add. Then you can specify two source registers. So the contents of the two source registers will be added, and that will be transferred to x1. Here again, a register move can be accomplished if this is the 0 register. Then essentially we are moving the contents of this to this. So as we can see, there is this nice trick that is packed in here, which is that if the first source register is 0, it is tantamount to a regular immediate move or a regular register move. That is exactly what it is, nothing more than that. Otherwise, it's a simple add instruction. So the other question is that can I load an immediate directly into a register, right? That is the main question. So RISC-V supports, in general 12-bit immediate. So this immediate over here is 12 bits, right? That is because you need space for other registers. So the maximum space that we can afford in this case is 12 bits. But there is an LUI instruction that can load a 20-bit immediate. So in a certain sense, this is what is being loaded, and this will be loaded in the upper 20 bits. So if this is a 32-bit field, whatever is being loaded, right? So let's say count from 1. Makes our life slightly easy. So then this will essentially load it here. So the rest of the contents from 1 to 12 will remain as they are. It will get loaded here. The reason being that 1 to 12 is something that we can anyway kind of access and modify using the add instructions. So any move is basically moving it to the lower 12 bits. That is why the load upper immediate LUI instruction essentially targets the upper 20 bits, which other instructions like the add instruction is not targeting. For example, if we do LUI x1 5, the x1, we will load the value 5, no doubt, but that will be in the upper 20 bits, which is tantamount to left shifting 5 by 12 positions. So we take 5 and we kind of left shift it by 12 positions and bring it here. And 5 is 101, so this becomes 101, and then the rest all are zeros. So what we see here is that if I want to load 32 bits into a register, it cannot be done via a single instruction. That is not possible. That cannot be done. So I need two instructions where maybe I'll use an add or something for the lower 20 bits and then an LUI for the upper 20 bits, then only it can be done. Of course, many times, this appears to be a bit too much. But well, this is the best that we can do. This is a limitation of the instruction set. That is why a pseudo instruction has been provided. A pseudo instruction is like a directive to the assembler, and in reality, it resolves to multiple machine instructions, in this case, 2 machine instructions, where you create a LI load immediate pseudo instruction where a full 32-bit immediate can be loaded into a register. But again, this is not translating to one machine instruction. It is translating to 2 machine instructions. One loads the lower 12 bits, one loads the upper 20 bits. Also, kindly notice, if you have not noticed, that in the first case we are using the regular numbers x1, x2, x3, and in the other case we are using the mnemonic, which is T0, temporary register 0, and both can be used, right? So we have also used both in these tables, but in the codes we have only used the mnemonics because that is the right thing to do. And automatically, if you use mnemonics, you will start following the register usage convention. That's why it's always good to use them. And it is also always good, if assembly code is being written, to use the pseudo instructions that the assembler is providing to make life easy. But bear in mind that this will resolve to multiple machine instructions after the assembler has done its job. So we are now here looking at our first piece of RISC-V code, assembly code. And this has been beautified. So this is the output of what the Carbon app gave me. So in this case, I want to add 2 large numbers, right? This difficult looking thing and this one. And then I would like to store it somewhere in some register. So in this case, what we do is that we realize that a reasonably good starting point is 4096 into 100. 4096 should be a familiar beast up till now. So 4096 is nothing but 2 to the power 12, right? So it is 1 and then 12 zeros. So basically, this should ring a bell at the moment. that in a 32-bit field, the lower bottom 12, the least significant 12 are all zeros, and then you have 1. So what we do is that we load an upper immediate of 100. So the moment we load an upper immediate of 100, this actually becomes 409600. And look at the first number, it's 409932. So if I subtract, then what I will get is 332. So I will do an upper immediate load here in T0, which will load this value. Then I will add 332 to it with the add I instruction. And the moment I have done that, then I add this to T0. So the new value of T0 contains this. Similarly, 409823 is not very far off. I do exactly the same with T1. And in this case, I add 223. So my T1 contains the value 409823. Finally, what I do is I use the add instruction to add T0 and T1, which are nothing but these two values, 409932 and 409823 respectively, and store the result in T2. So this is an interesting use case where the LUI instruction has been used, add-I has been used, and add has been used. So I can do the same, okay, using the li sudo instruction. So I didn't, in this case, I don't require those multiple instructions. My life is slightly easier. So I use the sudo instruction, I do li t0, so this completely comes in t0. Of course, at runtime it will resolve to multiple machine instructions. Similarly, I use t1 and this constant comes into t1. Finally, both are added. The moment both are added, the result can be saved in t2. So you can clearly see the human effort that this is saving. Now, if I look at the subtract instruction, so of course I would, along with the addition, so we have looked at add and add-I. Now I'm adding the subtract instruction here. So the subtract instructions, mind you, I don't need sub-I because the immediate is signed. But the subtract instruction is needed to subtract x2 minus x3 in this case, or x3 from x2. So sub is needed, and this is a legitimate instruction. So let me just compute 4 plus 5 minus 19. This is not very hard at all. So what I do is I load 4 into T0. I already know how to do it. The way that I do it is that I use the add-I instruction and I add 4 to the register 0, which basically transfers 4 here. Then 5 I add to 0 to transfer it to T1. I add them, I get T2. And then I want to subtract 19, but as I said, I don't have a sub-I instruction. I don't need it. Instead, I use the add-I instruction and I just add minus 19, which is tantamount to subtracting 19. So in this case, I add minus 19 to T2 and the result is in T2 itself, which is the final result. So let us keep going further. Let me now consider the quintessential problem of swapping two numbers that are in x1 and x2. Again, you will see that the 0 register, x0, will play a strong role. It always does, or at least it is appearing to always play a role. So in this case, what I do is I transfer the value of x1 to x3, and the easiest way of doing that is I add x1 to x0 and then it comes to x3 directly. Given the fact that the value of x1 has been saved, I transfer the value of x2 to x1, again via the same mechanism by adding it with x0. Given the value that x1 now has the swapped value, it is time for x2. So x2 gets the old value of x1 which was stored in x3, and again using the same mechanism, right? The add mechanism, add with the 0 register, this is transferred to x2. So this is a quick and easy way of actually swapping the values in two registers. So let's continue our journey. So now we will discuss multiplication and division. So multiplication and division broadly follow the same format. So we have mul, div and rem. Mul for multiplication, div for division, rem for remainder. And then again same destination register. So you multiply x2, x3, result is an x1. x2 divided by x3, result here is an x1 as you can see. And divide x2 by x3, integer division, the remainder is an x1. So this is all integer division. And if you would recall, both multiplication and division instructions are part of the M extension, which is technically not a standard extension, right? So this extension, I mean, it depends on who you're asking, but this is not part of the base instruction set, but it is part of the general instruction set. So that includes I, M, and A. So multiplication is kind of special because if you are multiplying two 32-bit quantities, the product would need 64 bits to store. So that is why there are two variants of it, multiplication H and multiplication H is for high and U which is for unsigned. So always H is for high, the upper bits, and U is for unsigned in case we are doing unsigned multiplication. So these instructions can be used. So you multiply them and then this instruction can be used to both multiply as well as compute the upper 32 bits. As well as compute the upper 32 bits. So the upper 32 bits, when they are computed, we would need obviously a different instruction, which is mul-h or mul-hu, depending upon whether we are doing regular multiplication or unsigned. Now here is the greatness of the RISC-V ISA. So as I said, there are these small things which sort of make the ISA special. Let us say that I want to multiply two 32-bit numbers and get the 64-bit product, right, in one go. So it is true that I will issue two instructions, mul and mul-h. Mul is going to give me the bottom 32. So let's call it 32 minus. And mul-h is going to give me the top 32, which is, let's say, 32 plus. Now this sort of sounds unfair that to compute the 64-bit result, which the hardware will have anyway, I need to invoke two instructions. This is not fair, right? Because after all, it's the same single multiplication, right? It is just that my output is not fitting within 32 bits. That is why first time I extract the lower 32, the next time I extract the upper 32 bits, which makes me do twice the amount of work. Does not sound very efficient. So what the RISC-V specification says is that the hardware should dynamically recognize that mul and mul-h are two sort of consecutive successive instructions and they are multiplying the same thing. If that is the case, it will sort of fuse them to a single instruction, do one single multiplication and write the results to two registers. The first one is the output of mul, the second is the output of mul-h. So in this way, only one multiplication will be done, but the entire 64 bits will be written in two registers. The first register will have the bottom 32 bits and the second register will have the top 32 bits. So this is one way of kind of saving one multiplication, which is a reasonable amount of work given the time and power that is involved. So division is slightly tricky, right? If you see multiplication, there was no issue. Signed multiplication, unsigned, no problem. The only trick here was the 64-bit thing. But division, there are more tricks. Okay, so the first thing is that unsigned division, no problem. 4 divided by 3, positive numbers, quotient is 1, remainder is 1, no problem. The question is, how do we define what is the semantics of the remainder when either the dividend, which is the first quantity, the one that you are dividing, and the divisor, the second quantity, one that you are dividing by, if one of them is negative, what do you do? That's the question. So, in a sense, the standard sort of semantics here is that you round towards 0, which is basically the sign of the remainder is the same as the sign of the dividend. So, let's look at this. You divide 4 by minus 3. So, if you divide 4 by minus 3, then you can have kind of two solutions, right? So, this could either be minus 3, right? Right, minus 3 into, sorry, minus 1 plus 1, or it could be minus 3 into minus 2, right? So that will make it plus 6 plus minus 2, correct? So in this case, this is 3 plus 1, 4, right? And in this case, it is 6 minus 2, which is 4. Because the final result has to be 4, because 4 is the dividend. So clearly what we do here is that we would like to essentially take that quotient here, that in a sense is taking us towards 0. So minus 1 is more towards 0. So we choose this, right? So we choose this, so then the remainder becomes 1. Similarly, let me divide minus 4 by 3. So this would basically become 3 times minus 1, which is minus 3, plus minus 1. The other solution would be 3 times minus 2, which is minus 6, plus 2. So in this case, one of the quotients needs to be chosen. Again, we choose that quotient which is towards 0, which is minus 1. So that is why we choose minus 1, and the remainder here becomes minus 1. So the remainder becomes negative, right? This is another thing that we need to keep in mind, or we need to bear in mind. So let me create some space for myself, and let me do a little bit of erasing, and then I'll come back. All right, so now we have the last case, which is minus 4 divided by minus 3. So again, the choices in front of us are again the same, minus 3 into plus 1, plus minus 1. And the other choice that we have, right, is minus 3 into plus 2. So we'll make it minus 6 plus 2, which is minus 4. So it's minus 3 minus 1, which is minus 4, minus 6 plus 2, which is minus 4. Again, we take the quotient towards 0, so that will be plus 1, right? And then the remainder in this case will become minus 1. So just if you have not noticed, the sign of the dividend and the sign of the remainder is always the same. This is plus 4, positive, 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 negative, 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 negative. So the sign of the dividend and the sign of the remainder is the same. And this is the classical rounding mode that integer instructions in RISC-V use. So here also the same trick can be played, that consecutive division and remainder instructions, where clearly the dividend and divisor are the same. So you have a div and you have a rem and you are doing the same operation. both of them can be fused. They can be fused into one, and clearly the results go to different registers following the convention that we just showed. So let's say I want to multiply 3 with minus 17. So what I do is that I load 3 into T1 minus 17 into T2. We are experts on this now. So this is just 12 bits, right? So essentially it is, 12 bits. It is not very hard to find the range, which is minus 2048 to plus 2047. So 4096 numbers. This is the range. This is well within the range. So then I load it in a register, then I multiply them, and the result is in T3. Let me make my life slightly more difficult. Let me compute 12 cube plus 1. Well, again, the first thing that needs to be done is that we need to load the registers with the requisite values. So in this case, what we do, so we have already seen the same script playing several times. So we load 1 in T1, 12 in T2, 12 in T3. So what we do is we set T3 as T2 times T2. So on hindsight, this line was not required, so I'll delete that. But T3 is here T2 square, and then I multiply T3 with T2 again, and then this becomes 12 cube. I add 12 cube with the value stored in T1, which is 1, store it in T4. So T4 becomes the value 12 cube plus 1. So let us now look at another problem, similar one, dividing minus 50 by 3. So here we load minus 50 into a temporary register, 3 into one more T1. So this is the advantage of using mnemonics, that we stick to the register usage convention. This does not allow us to kind of deviate from it. So the first is a regular division where we divide T0 by T1, store the result in T2. That's the quotient, and then the remainder is stored in T3. So as we have argued before, the hardware recognizes that the division and the remainder instructions are consecutive. So they are dynamically fused to be one instruction in hardware, one division. So next we can take a look at the bunch of logical instructions that are there, logical and shift. All of them look similar, so I am not separately introducing them. So you have and I, or and or I, same format as add. XOR and XOR I, shift left logical, shift right logical, shift right arithmetic. So these three we have seen. Shift left arithmetic doesn't exist, right? So that nobody has that. And then their immediate variants, SLLI, SRLI, and SRAI. So we will use this to indicate right shift arithmetic. So the generic format of shift instructions is like this, the same as add. RD, RS1, R2, or RD, RS1 is first source and the immediate. So again, a couple of examples are due, reasonably simple ones. We have been seeing them throughout. The bitwise OR of A and B, well, load 4, let's assume A is 4, B is 1. So load 4 into T1 and OR it with 1 using the OR I, or with immediate instruction. Compute T1 is equal to T2 plus T3 times 4. So the moment we see times 4, we can see that a shift left can be done, right? So times 4, we can reduce the strength. There's no reason to have a multiplication if the same is achievable using regular shifting instructions. So in this case, we initialize the value of T3, initialize the value of T2. we shift it left by 2 positions, which is tantamount to multiplying T3 by 4. And we store the result in T4, which is then added to the contents of T2. And the result is in T1, and T1 is our final answer. So here clearly the moral of the story is that multiplications are slow operations. Left shifts on the other hand are much faster and are always preferred as long as a power of 2 is involved. So we have now completed the first part of the lecture where we touched upon RISC-V, the introduction, the need for RISC-V, right? So obviously the need was, as you can see, it's a reasonably sophisticated instruction set. So there were technical reasons because we have, flavors and variants and extensions, right? And of course, there was a strong legal aspect that it is an open instruction set. It does not have the kind of license fees that other instruction sets have. So it is actually meant to produce open hardware. So in a certain sense, it's like the Linux of hardware, right? The GNU licensing model for hardware. So that is where the RISC-V movement, and I'm using the term movement deliberately, because the aim here is to sort of look at a different kind of a model, something that open source and free software did in the world of software. This is kind of like that. And then we looked at integer instructions, we looked at the registers, we looked at the very important role that the 0 register plays, in the sense that you don't need move instructions, you just need add instructions. That's all that you need. So then we looked at all variants of this. So now what we will do next, which is in the second lecture, is control transfer and memory. Then we will move on to discussing floating point instructions and encoding the instruction set. So we always look at this at the end. So encoding the instruction set basically would mean, appreciating how whatever we have studied is fit within 32 bits. So I will see you in the second lecture of this RISC-V series.